my talk is about a bit of a strange field, tangles. Has anyone heard about tangles in graph theory so far? Not a single person. I'm really surprised, because tangles are a very prominent concept in theoretical graph theory. So if you're deep in mathematics and graph theory, tangles is a concept that apparently is used quite a lot. And the way this project came about is, I used to work in Hamburg for some time, and there's a graph theory group by Reinhard Distel, which is a quite well-known group. And we were sort of in touch, and we chatted. And eventually he said, you know, there's this abstract concept. We use it all the time when we want to prove our theorems, but we think there is some potential for applications. So, and then we started to collaborate, and now that's the outcome of this or the first outcome of this collaboration. We are going to talk about clustering with tangles. And another side remark, my daughter made this title slide. So in the pandemic, we got used to, I had to teach a lot online, and she always made the title pages. So whenever now I'm going to give a presentation, she wants to design the title page. There we go. So formally, this is a collaboration between a group of people in Tübingen, the red ones on this slide, and a group of PhD students in Hamburg. So before going into the math, let me just start with an example. So assume you have some kind of questionnaire setting. You have a number of people and persons, and you have a political questionnaire, so you ask them about their whatever political preferences. You ask a lot of questions, and each of the questions has a binary answer, so you can answer yes or no. And now what you might want to do is you want to identify sort of groups of people who share similar mindsets. And the idea, and this is what tangles are about in a very abstract sense. So the main characteristic of this problem is we don't want to make any hard assignments, in a sense like this is really a social democrat and this is a Republican and this is whatever person. And we also don't want to make hard assignments saying like a social democrat always answers this question in a certain way. We want to do a rather soft characterization of this political opinion spectrum in some way. And this is what tangles can provide. So to get the tangle approach working, the first observation is that if you have a question and you have people who answer yes and no, this is going to give you a partition of your data set, right? So we are now going to see many plots. The dots are always going to be the persons, and then you have a line indicating that some persons answer the question with yes and some other persons answer the question with no. So each such question in your questionnaire induces one such partition. And now if you have a full questionnaire, you have many such partitions. So you have a data set and there are all kinds of partitions. And maybe some questions are really informative and maybe some other questions are completely useless. So I don't know, asking about whether you wear glasses or not probably doesn't have anything to do with your political opinion and so on. So you have questions of different levels of informativity. Some of them might be nearly random and some of them might be very informative. And now the question is, so this is the data set you get as a machine learner. So you have participants or more general objects that you want to group. And you have these weak partitions where each of these partitions just gives a bit of information about the cluster structure, if you want, or the group membership of the people. And now the question is, how would you recover or get out the mindsets from such a data set? Now the intuition of tangles is the following. So the tangle approach says to each such partition you need to find an orientation. And for now we keep it really informal. An orientation is just something, you just say here we have this blue partition and the blue arrow here just indicates a direction we want to point to. And now for each of the, so we have now this is like each plot on this slide is the same data set but different orientations. So in this top plot here we just put the orientations as indicated by the arrows. And now what you want to say is, like in this set of orientations, these kind of orientations point towards a group of people. So if you look at this plot here, the yellow shaded area here is the one which is in the intersection, like in this image of the half planes that are indicated by these cuts, right? In general, of course, it's not half planes, everything is discrete, it's a discrete set of points. But so what you would like to do is to identify a group of people which share the same mindset, you want to find orientations of these partitions such that all the orientations jointly point towards a large enough group of people. And this later on is going to be called a consistent orientation, and we need to make a formal definition for that. The first observation is here that given the same set of persons and partitions, there might be many such orientations. So here we have 3 different ways to orient the hyperplanes in these figures, and they all point to different sets of people. So here we identify this yellow group here. Here we changed some orientation, I think the green one, so we point out to this group, and here we point out to another group. So given the separations, you could potentially discover many groups in your data. That's the first observation. And the other one, for which I don't have a figure here, but later on, is, of course, there might be orientations which don't point to anything, where this intersection is either completely empty or too small to be considered a cluster in your analysis. So far, so good, the intuition? Okay, and this is sort of the intuition that we want to do with tangles. And now there's this formal mathematical framework. It looks, so in the mathematics literature, it all looks different and much more complicated, so we try to reduce it to what we actually still need to make it work for applications. So if you would open a math paper, it would look a bit different, but this is now how we distilled it down for what we need. So what you always have is, you have a set of objects. They could be participants in a study, or they could also be vertices in a graph. That's why I called them V here. So but a finite set, so you have a finite set of objects, N. And you have a set of M partitions. And each partition is just a bipartition, so it splits your vertices into exactly 2 disjoint groups. And these are the things that are given. Of course, in applications, we need to talk about how do we get to these partitions, but assume for now they're given. Now we say an orientation of a partition is just something that selects one of the 2 sides of this partition. So really, as in the figures we have here this partition, and we just say the partition here is oriented towards A, and not towards A complement in this case. So by selecting one of the 2 sides, you can always indicate the orientation of the partition.
Sorry, can you, let's say, maybe not in every framework, you could cast this also in a geometric setting?
I'm sure you could also cast it in a geometric setting. We didn't try, but I'm sure it would work.
With hyperplanes and you do intersections?
Yes, I'm sure you could try to do that.
In this case, it's more just a general...
Yes, so for now, so the question was, can you also cast it into a geometric settings where you really have hyperplanes and some geometry in the background, or maybe a manifold or so? I'm sure you could do that. And the approach, I mean, you would then need to adapt it maybe a bit. So what we have on the slides here is all for finite sets, but I think there's an obvious way in which you could try to extend it to continuous settings or geometric settings. Okay, so now we know what objects are, what partitions are, and what an orientation is. And now here, this is the central definition of the whole tangle approach. Okay, so we're given the set V of objects, and we're given the set P of partitions. Anything but fixed for now. And now we consider one orientation of all the partitions in P. So we now have these partitions, and to each of them we assign one orientation. And sort of the set of all these oriented partitions we simply call curly O. And now we want to say the chosen orientations, are they consistent or not? And the intuition is, do they point to a large enough group of people? That's what we want to say. And the condition is now a bit technical, and that comes out from the math literature. What we need to do to say whether a partition is consistent or not is the following. We need to select 3 particular cuts so we have like 100 cuts. We select 3 of them, look at where they point to, and these are now the sets A, B, and C. These are the 3 sets where these cuts point to. And then we want to say, in the intersection of these 3 cuts, there are at least a number of objects. So the absolute value here just counts the cardinality of the set. And let's maybe go to a figure. I think it's easier. So here we have a set of points, we have a set of cuts, and we already fixed orientations for all of these hyperplanes. And now we want to ask, is this way to orient all the hyperplanes, this joint way to orient them, is it consistent or not? And the answer in this case is yes. And how do you see that? Now you need to look at all possible choices of exactly 3 of these cuts. So here I just picked 3 of them. And now you check at what is in the intersection of the 3 of them. And you find this yellow area here. And you say, are there more than, so you have a parameter A, which is called the agreement parameter. You fix it and say A is 3 is, for example, in this figure. And you now ask, are there more than 3 points in this intersection? Yes, good. And then you choose another 3 hyperplanes from the set of all your partitions. You check if you look at the intersection area, are there more than 3 points in this intersection area? Yes, good. And you do that for all possible choices of 3 hyperplanes in this cut, in this set of cuts. And if this condition is true for all of them, then you say the orientation is consistent. And somehow to also get the intuition what is going on here is, if you look at this figure here, so here is this one upper triangle, that's sort of the place where every hyperplane here points to. So even in the intersection of all of them, you find a number of points. This would be the group you want to point to. But this kind of definition here makes it a bit softer in the sense, maybe there is nothing in the intersection of all the cuts, maybe because if one cut is sort of a stupid cut, then it sort of wouldn't work. And this kind of definition makes it a bit softer. Okay, let's maybe just go back one slide. Say it again. So we have the set of vertices, we have the partition, we fix an orientation for all of these cuts, and then we say this joint set of orientations is consistent if for any choice of 3 hyperplanes, the number of points in the intersection is larger than A. So A is a crucial parameter in this whole framework. It's called the agreement parameter. And now any such consistent way to orient the hyperplanes is called a tangle of the set. And now these are the objects we're after. Oh, and here, sorry, I forgot to show that. So here on the previous slide, we have a consistent orientation because whatever choice of hyperplanes you pick of 3, it's going to have enough points in the intersection. Here we have an example of an orientation that is not consistent because you find 3, so it's now the negation of the statement. Previously we said for all choices of 3 hyperplanes. Now the negative thing is you need to find a choice of 3 hyperplanes such that there are not enough points in the intersection. And here is an example for that. So this way, here in the top part of the figure, of orienting all the hyperplanes would not be called consistent. Yeah.
Some intuition why 3, not 2 or 4?
Yes. Well, no intuition, but there's a reason. So if you would choose 2, so that comes from the mathematical framework. If you would choose 2, then you would find so many tangles in all these data sets, exponentially many, that this is completely useless. So there are theorems that in the math literature that if you choose 3, then essentially the number of tangles is sort of linear in the number of data points that you have. And this is what you also would have to have in clustering. We don't want to have exponentially many clusters. This somehow doesn't make sense at all. I mean, in the worst case, we want to have each point in a cluster which would be linear. So if you would choose 2, this whole thing would explode. If you choose more than 3, and essentially 3 is the right thing because it gives you the richness you need from mathematics. If you choose more, you don't gain anything. And for us, it just means a higher computational burden, and that's why we choose 3.
Is it related to the dimension of the embedding of the Sorry.
Yeah, I don't think so. I think this is not really related. I mean, and many of the things we do here are not related to any dimension. It really, I mean, I think you can in certain cases maybe relate it to the dimension, but it's not so, I mean, it's not so obvious, and it also depends on how you choose the cuts. Yeah.
You said it's linear when we choose only 3 participles. Is it for ID points or is there a structure for?
So say it again, is it for?
So you said it's linear when we choose only 3
Yeah.
Is it for ID points? Or
What do you mean by high D points? So this is just a very general statement in math. If you choose 3 of them, then there's a bound on the number of tangles you can find. So there's no relation to the geometry whatsoever. Okay, now we want to talk about algorithms and simulations. And as Solveig has done lots of this work, I just thought maybe Solveig wants to present this part, and then I come back for the theory part.
Okay, so we kind of know what a tangle is now, or at least I hope everyone knows what a tangle is. And we like them because they point towards cohesive structures in the data. But we don't know yet is how to find them in our data. So like before, we just assume we are given some data points and we're given a set of cuts. And the naive approach is we just check all the 2 to the power of m partitions, and we check if they're consistent. So we check all choices of 3 cuts of 2 to the power of m partitions. It's probably a little inconvenient. So we try to come up with a more clever approach. And I want to go back to this figure for a moment. If you look at the bottom figure right here, we see this is an inconsistent orientation, so it's not a tangle. And clearly, no matter how many cuts or orientations we will add to that, this will never make the orientation consistent. So we cannot get a consistent orientation from a previously inconsistent one. And the opposite kind of holds if we look at a consistent orientation, like both of these. We can take any subset of orientations and it will still be a tangle. So no matter which cut we remove or which orientation we remove, it's still consistent, it will still give us a tangle and point towards a cohesive structure. So this means we can build tangles iteratively. So we can build larger tangles or tangles considering more cuts on tangles considering less cuts. And so we kind of like want some ordering, know which cuts are very useful and not. We start with the useful ones and we try to orient them in both directions. And if it's possible, we continue with the next cut. And this will give us some sort of tree. And I'll go through an example in a second. But the important takeaway is, as in this figure, as soon as we reach a point where the orientation is inconsistent, we can stop. Like we don't need to check for any additional cut anymore because we know we're not going to make it a tangle anymore. Okay, so if we want to order our cuts by usefulness, we need some measure to order them, and we introduce a cost function. I think the intuition is relatively clear. We think cuts are useful or good if they separate dissimilar objects, and we think they're not that useful if they separate similar objects. Like the blue bipartition, no matter which direction we would orient it, it will give us barely no information about the cluster structure. So we will want to give this a high cost, and the red one, for example, we would want to give a low cost. And what we usually do is, given any similarity function of our data points, we just average or sum over all pairs from different sides of the cut. So we take all possible pairs from different sides and we sum or average over them. Clear? Yes?
So you have a graph on top of the answers to the questions?
You mean as you can interpret the similarities as a graph? You can interpret it this way, but it doesn't really matter. We can have arbitrary similarity functions, and depending on the objects where they come from, you can include domain knowledge, for example, in there as well.
In addition to the answers to the questions, you also have features, let's say, for the people who answer the questions.
Usually the questionnaire setting is somehow a weird case, as we can use the answers to the questions directly also as a similarity measure of 2 persons, like comparing how similarly they answered. We can have a distance on that as well. But usually it is very independent, or it can be independent of the cuts you have. So you can have a set of cuts and you can define a similarity function independently of that. And this is just what we usually do, as it's simple. If you have a similarity function on your points, you can just use that. If you have some other cost function on your bipartitions, you can also use another one. But this is clearly a bias you put in there, right? So as soon as you fix this, you kind of like define what you assume to be similar and what you assume, like what you want to be separated and what you do not want to be separate. Okay, so here's a small example. We're given a set of data points and we're given a set of cuts, and these are already sorted according to their cost. So P1 is the cheapest cut and P7 is the most expensive cut. And we're given some agreement parameter. In this case, it's 10. It's a little arbitrary, but it's some small number capturing some cohesiveness in the data. And we start with partition 1. And as we can see in the bottom part right here, there are less than 10 points. So orienting P1 downwards, choosing this side is not consistent. But pointing it upwards, here there are more than 10 points. This is consistent, and we can have a path in our tree visualizing exactly that. So this one direction is consistent, we add a path, the other one is not, we don't add the path. So this already is a tangle on a very small set of cuts. And we continue with the second cut. It's the same game, lower part, less than 10 points, it's not consistent. The upper part is, in this case, we also have to check the intersection of P1 and P2, but it's large enough, we're happy about that, and we add a path in the tree, and we have a tangle of the set P1, P2 now. Now, cut 3 is a little more interesting, as there are many points for both orientations. So taking the intersection of P1 pointing upwards, P2 pointing upwards, and P3 pointing to the left is consistent, has more than 10 points, and we can add this path. It's corresponding to this direction, and it holds for the other side as well. Taking the intersection of the 3 cuts is consistent, and we add this branch in the tree. And yes?
So I have a question. So the problem that you're trying to solve is you're basically trying to minimize the cost subject to the constraints of you're only able to pick tangles, right? So
whenever I add something to the tree, like every node in this tree corresponds to a tangle. Oh, like every.
Is there a combinatorial optimization problem that you're essentially trying to solve here? That question makes sense.
I know, I don't know if I get the question.
Cost area, right? So the cost function that you found, are you trying to minimize the cost by choosing the partitions, let's say?
So I think, coming from tangle theory and graph theory, we usually consider all possible partitions of the set, like all of them, which is not really useful in practice, but we consider all, and we assign a cost, and we talk of a psi tangle considering all bipartitions up to some cost. And this is somehow what we do here. We don't consider all of the cuts, but every layer in this tree corresponds to cuts up to some cost. Does that answer what you meant?
Yeah, it just looks to me you're trying to minimize the cost function subject to picking partitions based on the answers, let's say.
Oh, I'm not.
Or maybe a constraint if they are tangles or not.
I'm not optimizing the cost function in this case.
Yeah.
So I'm given dataset cuts and cost function, and what I find here are all the tangles that exist in this set of cuts. There are different ways to find them. Like I could just check all possible orientations. I would find the same set of tangles. Like I'm not optimizing anything. This is just finding what is existent in the data. Yeah?
Do you use then the post to define the order of these tangles?
Exactly. Yeah, like how I traverse the tree is based on the cost, and if I would order them in a different way, I would probably not find it. So if I check everything, I would still find it, but if I have a different cost function, I would probably find something else. Okay, so we do this for all the cuts, and we get a tree like this, and we have like the leaves of our tree, we call them maximal tangles because we cannot extend them any further, and it could happen that I have a maximal tangle somewhere up here, as adding a cut is not consistent in both directions. So this could also happen at some point. But now we have all the tangles, and as we already discussed, they don't assign clusters to points. Like it would be kind of inappropriate to talk of tangles as clusters, as it's a more soft characterization as where they point to without making a statement about objects. So we need to post-process them in some way. And
do you find all the tangles like this, or do you find some?
I find all the tangles in my set of bipartitions. So given a set of points and given a set of bipartitions, I find all the tangles in that set. Coming from the definition from theory that we can only build more expensive tangles on cheaper tangles. I think that's the point with if I change the order, I could get something else, but this is the definition of tangle, that they're based on costs as well, and that I build more expensive tangles from cheaper ones. Okay, so we're looking at this structure over here, And there's several ways. Like this is existence. Like everything until now, it's just we find tangles in the data. And now how we post-process them, there's several ways to do that. And one simple one is we look at an object, for example, an object over here, and we just count the orientations that point to that object. In this case, it's, I think, 3 for an object in this area and 6 for an object in that area, like all of them. And we do some normalization, and we can also include the cost of the cuts, for example, if we want to include that. And we get a value that aims to capture the likelihood of a point to belong to the tangle we put here. And like I said, it's not really correct to talk about tangles as clusters. So we usually have a point belonging to a cluster or belonging to a cluster that corresponds to a tangle, or we say a tangle corresponds to a cluster, but I might say that wrong as well sometimes. Just beware, it doesn't really belong to a tangle. It belongs to a cluster that corresponds to a tangle. Okay, and we can do this for every point and every cluster in the data, and what we get is something like a soft hierarchical dendrogram. So this is the root, all nodes belong to the root, and then we calculate for all the nodes in our tree, or for all the important nodes in our tree, let's say like this, the likelihood that it belongs to the tangle, or like the cluster corresponding to the tangle. And I'm not sure how good you can see that there are some areas that are a little lighter down here, or probably here. So there are points that do not belong to a cluster with 100% probability, but something in between, and we have the soft notion captured in the soft dendrogram. And from here, it's not that difficult. We can just get a hard clustering by assigning every point to the cluster it belongs to with highest probability. Yeah? Okay. Then there's one really nice property about tangles. And if you remember the questionnaire setting from the beginning, or any setting where our cuts themselves are really interpretable, like this is like a medical setting, and we ask questions like, what's your age, and how tall are you, and are you a smoker or not, and what's your weight? Then on these branches between, there are several cuts. But probably we can see this here. Some cuts like P3 and P4 and P7 kind of like do the same job. So we can use tangles to identify important cuts for separation, like characterizing cuts for a cluster. And they will give us the answer to that in the tree. So on each branch, we can find characterizing cuts, and we can kind of like develop an explanation for our clustering using tangles. If the bipartitions are interpretable, the output's going to be interpretable as well. Yeah? Great. So we like tangles because they have many good properties. And we did a lot of simulations to verify that. And I want to show some experiments on simulated data. So the first is stochastic block model. I think don't have to explain that. We have the inner cluster connectivity P on the bottom, and then we have between cluster connectivity on the left. And we measure the performance by the normalized mutual information, and we just compare it to spectral clustering in this setting. And we can see that we do perform comparable on the simple task. Another experiment we made, this is on a mixture of Gaussians, and we want to see the runtime of tangles, because many points, many bipartitions, we want to know how it performs, and we see on the bottom is the number of nodes, and we have the runtime in seconds on the y-axis, and we compare to k-means in spectral clustering. So the thing we want to notice is relatively fast. I think we're comparable to k-means and way faster than spectral clustering. And then what we want to check on the top is basically a sanity check. We're still comparable to what these algorithms do. Yeah?
How do you construct the partitions here?
In this,
the previous example with the SBM.
yeah. So in the SBM setting, it's a local search heuristic for the min-cut. I don't know, probably some know the Kerning and Ling algorithm. It's a local search algorithm which tries to optimize for min-cut, and we just do random initializations and early stopping to get like a set of relatively messy initial cuts. It's fast. And for the Gaussian of mixtures, what we do is we project onto one dimension and then find two means basically, or cluster on one dimension, and we do that a lot with random projections, and find a quick and dirty set of bipartitions.
So rather than hyperplanes.
Again?
Hyperplanes.
Yeah, in this case. But this is just one choice for settings like this. Ideally, or in application, you often have better cuts or better intuition about what good cuts could be, and you want to capture information. Like if you have information about your data, you want to put that in there.
And similarity, what's similarity here in the products? What do you use for the similarity?
I think in the spectral clustering, it's just the Euclidean distance, and in the Gaussian mixture model, and we use the cut cost for the graph. Okay, and the last experiment I want to show is also about runtime, but this time how it scales with the number of cuts. And we show two experiments here. The one is 5 clusters and the other one is 4 clusters. So the number of clusters is kind of related to how many cuts we would probably need to separate the data. And basically what we want to see, and what we also do see, is it saturates rather fast. So we don't need that many cuts to actually separate our data. Clearly, this somehow also depends on the cuts we're looking at. But it's the same mechanism we used before. So in the graph setting, we use the local search heuristic. And in the mixture of Gaussians, we use random hyperplanes. And I mean, what we can see here as well is that the runtime with the number of cuts looks almost linear. So it's not as bad as we would probably think, considering that we have to compare all sets of 3 cuts. So the tree branches off pretty fast, and so we don't have to completely search the full tree. Okay, so Rick is going to talk about the rest.
Okay, so what we've seen now, I mean, we built this framework. It seems to work in practice, but now all of us are theory people, so you actually want to know, can you prove something? Like, I mean, it's nice to have figures, but I want to know whether it works, at least in simple cases. So what we did, and in fact, that was the first thing we did before running all these simulations, we wanted to know what kind of theoretical guarantees can you prove. And now I have 3 slides with theoretical guarantees, each one corresponding to a different model. The first one, well known in this community here, is the stochastic block model. So the model we now have is we assume we have n vertices in k clusters drawn from the stochastic block model, where the within cluster probability is p and the between cluster probability is q. And we assume that p is larger than q. And we want to now look at data from this model and see whether we can recover the blocks. Now, the important question that you also asked is, what are the cuts we use? And in this example, we do what people in theory often do. We simply assume we have all possible graph cuts, all the 2 to the power of m many cuts, 2 to the power of n in this case. And we have the standard cost function for cuts, which just counts how many of the edges would be cut if you look at take a look at a partition. And now we maybe first look at the theorem, and I'm going to try to guide you through. So this is so the theorem, as I've written it here, is for the case of 2 clusters. You can also have it for more clusters, but this is just for 2. So the first assumption you need to make is that the within connectivity P is in some sense large enough compared to the between connectivity Q. I mean, any guarantee on stochastic block model would have a condition like that. Maybe the first note I need to say here, we did not try to make these bounds tight in any way. It's just a proof of concept. There's nothing, I mean, I'm sure you can improve any of these bounds immediately, but that was not the purpose. But it makes sense. You need to have the within cluster connectivity large enough compared to Q, and also compared to the agreement parameter that tells you how large are the clusters you want to find in a certain way. And now what we do is, I mean, in theory, we started with a set of all possible graph cuts. But now what we do is we only look at graph cuts which up to a certain cost function. So what we now do is we define a threshold psi and say, let's look at all the cuts up to this threshold psi. And the threshold always talks about the cost function of that cut, right? So we look at low cost cuts up to a certain threshold. And now the theorem goes as follows. If this parameter psi that we chose for what is the boundary to which we go with the cost function, if this satisfies some, it's not too low and not too high, and that's a complicated expression here which I didn't put on the slide, but if it satisfies certain guarantees, then you can prove that the ground truth blocks in the stochastic block model exactly correspond to tangles. So if you have two clusters in your block model, you would find two tangles and they would correspond to these blocks. So that's exactly what you want to find. Maybe you could improve the conditions, but this is the kind of theorem. There's also an opposite theorem that says if the within cluster connectivity is not high enough compared to Q, then nothing is identifiable anymore and you would just find one tangle. So the tangle approach could not distinguish anything, it would just find one large tangle and that would be it. Okay, so this is, I mean, it's just a sanity check, but it says if you have a stochastic block model and you have parameters in a reasonable range, this approach is going to recover the blocks. So in machine learning, sorry.
Yeah, why is there a lower bound? Like
on
psi?
if
the upper bound I can understand, but why would you need a lower bound? Let me just think. So the question was, why is there a lower bound? Why can't you do it? Like, I mean, if psi is 0, for example, you don't have any cut in your set. So you need probably a number of partitions to be able to identify the block. Because if you just have one cut in your set, then this might not be the cut you're looking for, and then you probably can't identify it. So sorry.
Yeah. So I think the lower bound, or especially the psi bound, is cost dependent, and usually the cheap cuts, if you just consider cut cost, the cheap cuts are on the outside of the data, just pointing to the middle. So we need to make sure that the centering cut, the one actually separating two clusters, is within this set of cuts, and that's the lower.
I don't know whether everybody got that. So if you just have a random graph drawn from a stochastic block model, you typically have these kind of, you have lots of connections here, and then there's the other class, and few connections here, and you might have this outlier kind of thing. And if you just have very low cost cuts, then you would just see this guy, and you cannot identify the block structure. So the costs need to be large enough such that you include the cuts, maybe it has two edges, that are also between the classes. Okay, stochastic block model is sort of the very simplest of all models on graph clustering, so it's fine to be able to solve that, but maybe there's more in the world. So the obvious next thing everybody looks at is Gaussian mixtures. And again, we look at it in a very simple scenario. There's nothing really, it's not a tight bound, definitely not, but it exhibits the correct behavior. So now assume we have n data points in RD, sampled from a mixture of two Gaussians. One mean of the Gaussian is mu, the other mean is nu, and they have the same the same standard deviation and unit covariance matrix. So really the most simple of all cases. And now the interesting question is again, what are the cuts that we are going to look at? And in this example, we chose all axis parallel cuts. So you have all cuts in this direction, all cuts in this direction, and then for each dimension, you look at all the axis parallel cuts. And the cost function is again the standard cost function based on the Euclidean distance within the space. And now the theorem, again, this is just a sketch, looks as follows. So assume the agreement parameter is small enough. So remember, the agreement parameter is the one that tells you how many points you want to find in your intersection. And obviously it has to be small enough, because if you say I want to have all points in my intersection, you're not going to find something. So there's a constant which I didn't put on the slide, but if the agreement parameter is small enough, that's the scenario we currently look at. So that's one condition. And the second condition you always need in any of the statements about Gaussian mixtures is the means need to be well separated in a certain way. If the means are exactly the same, you wouldn't be able to find it. If they are too close compared to the standard deviation of your Gaussian, you wouldn't find it. And the condition we need in this work is the means need to be separated at least in one dimension by a distance larger than 2 times the standard deviation. Okay. I'm sure you could make this tighter and so on, but this one works. And the statement is now if these conditions are satisfied, so the clusters are well separated and the agreement parameter is not too large, then you will always find at least 2 tangles, 2 different tangles that point to the 2 cluster centers, either mu or nu. So
So this is one side of the statement. So there is at least two tangles which separate the two. And now the statement the other way around is, if the agreement parameter is large enough, again larger than another constant times the number of data points, and again the clusters are separated, then every tangle either points to mu or nu. So you would here have exactly the two tangles then, like combined with the previous statement, that point to mu and nu. And we need to have the agreement parameter large enough, because if it's really small, then you might discover like a bit of noise clusters, but as soon as A is large enough, these noise clusters would go away and you just see the right clusters. Okay? So again, this is not tight, but it's a proof of concept that tangles would do what you want them to do. And then we have a third example of theoretical guarantees, and I don't want to go through all the details due to time, but we now set up a statistical model for this kind of questionnaire scenario where you have people answering questions and you have mindsets, and sort of people in a mindset tend to answer in the same way. You can set up the model. It's sort of, I think that's the default thing that everybody in this room would come up with if you have a day or two and think about such a model. And the theorem again says, so here if the noise in this, P is the noise now, if the noise in this model is not too large, and again the agreement parameter is within a certain interval, then with high probability, again, you would find exactly the mindsets that you put into your data. Right? So these are, yeah, sorry.
Do you have the reverse direction also for this one? Or?
So this is in this sense, as I've written it here, or, so what do you mean by the reverse direction, that it doesn't work? Or?
You cannot, if A is too big, then you cannot distinguish.
I think we didn't formally prove, I'm not sure, did we prove the reverse direction? I think we didn't try it here. But I'm sure it would work as well. Yeah. Maybe not tight, like in the sense that, so the question was, do I have the other side as well? Like if A is larger than this, like this bound, then it doesn't work. I'm sure you can prove that. I haven't looked into it. No. So, I mean, to summarize these theoretical guarantees, what is really nice is we have guarantees in 3 different scenarios, which is surprisingly strong. So if you think about the clustering literature, for many of the algorithms, you just get guarantees in 1 or at most 2 of these scenarios, but typically not in 3. And also, I mean, we didn't like take 10 years to prove these guarantees. I mean, it was some work, but it's not like it's completely impossible. So it points towards just saying this seems to be a framework that is really general and powerful in a certain way. So that's what we take from this questionnaire, from these guarantees. Okay, and now, of course, the last remaining bit in such a talk would be, I mean, we have the concept, we have the algorithm, we have the simulations, we have the bounds. Now, does it actually work in practice? And this is where we are currently. So we have started some projects where we apply tangles to real data in collaborations with people who work with real data. These are all a bit preliminary results, and I just want to point out one here, which is in climate data. So what we have here is precipitation data. So I didn't know this word before. Precipitation is how much does it rain. I don't know whether everybody knows that word. I didn't. So what we have now is the data consists of time series at different points on Earth. So say here in Lumini, someone for the last 30 years measured how much rainfall did you have each hour of the day for the last 30 years. So you have a time series. You have it at Lumini, and you have it at Marseille, and you have it at Nice, and you have it at 40,000 locations on Earth since 30 years. So this is the data to start with. And now climate scientists look at this data and want to identify interesting structure. Of course, they know already a lot, but I mean, that's sort of the starting point we had. We want to identify interesting structure. So the objects that need to be clustered here are the locations on Earth. So in the end, we want to say, the points, I don't know, close to Marseille behave similarly maybe to the ones close to Paris, but not so similar to the ones close to China or whatever. Or maybe surprisingly close to whatever happens in China. I mean, these are the kind of questions you ask. Now, how do you do that? So the objects are clear, it's the locations on Earth. Now, what is the cuts? The cuts in applications are always the place where you bring in all your prior domain knowledge that you have. So in this case, climate scientists know that the interesting thing they need to look for are extreme rainfall events. It means on one day there was this thunderstorm and it rained like 20 times more than on average. And these are the things they want to look for. So now we defined cuts. And the cut is now, you can consider it like a little questionnaire that you ask at each location on Earth. And the questions are something like, is the number of extreme rainfall events in spring at this particular point on Earth larger than on average? And then like you can do it for different seasons. You already get 4 questions. You can do it for different months, like are the extreme rainfall events in January higher than on average, or in July? And you can also say in calendar week 24, is it larger than average, and so on. So you come up with these kind of questions. So in the end, we selected 200 such questions. And now you're sort of in this questionnaire setting. Each location on Earth answers these questions. You get the partitions, binary answers, yes or no. And then you can start looking at it and try to build tangles. And in this case, I mean, it's clear that you cannot really see anything that's going on here, but none of us is a climate scientist, so it doesn't help us anyway. But this is what comes out. So we do this, we take this data, we apply the tangle framework to these 200 cuts, and we discover 10 tangles. And this is something that's quite typical. Even though you have very many cuts, like 200 here, you discover a small number of tangles, 10 in this case. And the dendrogram that you get from these tangles is this tree, so it has like 10 leaves. These are the 10 tangles. And now, as a climate scientist, so this is the soft dendrogram, you can now look at it and see whether the group memberships make sense. And there are certain things that make sense a lot. I mean, you find southern hemisphere versus northern hemisphere and so on, so there are certain things that are obvious. And then there are also some smaller patterns that do make sense to a climate scientist, which I can't really understand, but it does exhibit a structure they would find interesting. I mean, in this case, they already know it, but that's also sort of the most basic of all application cases. The other good thing of this approach, and I really think this is nearly the most strong aspect of the whole tangle approach, is this interpretability. So now you can say, well, there are these 2 groups of different of tangles, of clusters, of behaviors, and they can be distinguished by whether they have extreme rainfall in summer or not. So this is the first branch. And then extreme rainfall in winter is the next one. That also makes perfect sense. So you have, it's sort of northern hemisphere and southern hemisphere maybe. And then the next cut is extreme rainfall in August. And now what's really cool about that is, I mean, we had 200 cuts in here. So to explain a cluster, you don't need to give the answers to all 200 cuts, which would be completely impossible. And somehow this would not be interpretable. As a human, you can't look at what happens in 200 cuts. So the cool thing about the tangles is that typically the depth of this tree is really low. So you need to look at maybe 5 of these cuts, and then you can explain all the behavior of your data. And this is really cool because if you think about how would you do that otherwise, you would try to build something, like if you wanted to have something like that, you could try, I don't know, something like a decision tree or so, but then the amount of the clusters you would get in a decision tree are not as flexible as the ones in a tangle, like in a, I don't know, if you look at data in RD, you would essentially get rectangular clusters from something like a decision tree or a spatial partitioning tree. And tangles, like, they're not just rectangular things because of this kind of soft group membership. So you can find groups that really have like very diverse structures, yet you can explain them by very few questions, as you could for a decision tree. And that's something that I really find quite promising. And now, I mean, I've attended the talks this week, and in the back of my mind, whenever I heard a talk, I thought about, well, is there some applications for tangles in what everybody has been doing? And here on this slide, I just put 3 of them, just to show you that really there is a lot of potential for applications. So Sophie, what you want, I mean, this is now all my interpretation, right? I didn't talk to any of those persons, and it could be wrong, but my interpretation of what everybody was doing is on this slide. So Sophie, she had graphs, and she wanted to distinguish groups of vertices according to functional roles they have in the graph. So is it some, and functional role was described by properties, maybe if you wanted, of the geometry of the graph, like does it have a high degree? Are there many triangles attached to this particular vertex? Does it have a low betweenness? Whatever. These were kind of the ways she characterized what she's looking for. Now you could try to do that with tangles. So the objects are the vertices of your graph. And what are the cuts? The cuts, now you introduce this kind of questionnaire game. You ask, is this vertex, is the degree of this vertex larger than 10 and 7 and 8 and whatever? So you introduce cuts which sort of ask these kind of questions. And then is the number of closed triangles larger, which are attached to this particular vertex, larger than 5? I mean, I make this up, but this is just to give you the story. Or is the betweeness smaller than 2? And then you're exactly in the tangle scenario, and now we can try to invoke tangles and see what happens. I don't have any clue, but this would be something you could try. Okay? And there was this other talk, Dimitri was here, I'm not sure, about brain connectivity by Dimitri. So he said he has 2 types of information on the brain. There's the structural information coming from how are the neurons really connected to each other, that's a graph. And then there's the functional characterization coming out of fMRI or MEG or whatever. And then you're looking for regions in the brain that do something similar or that are connected. And how would you do it with tangles? You would say, well, the objects, again, the vertices in your structural graph, so the brain regions or the voxels or whatever you take. And the cuts are now related to this functional data. So you have, and that's also a strength, so you might have different data modalities, and you might answer questions according to all of them. So you could, I mean, now, I don't know whether this would be a useful question, but you could ask, I don't know, I have this fMRI data, and people needed to grasp some objects, and now you could ask, was that region in the brain active when they performed this task, yes or not? And then you ask for a different task, or I don't know how you would measure it, but you look at your functional data and try to ask meaningful questions about this data. And again, you get cuts, and then you can do tangles. And now you can do that for, say you have fMRI data and you ask some questions, and then you have MEG data, and then you have EEG data. And typically it's really hard to combine all these different data modalities, because how should you do that? It's really complicated. But this kind of asking questions is something that's really easy. I mean, you have your basic objects, and you can ask questions about all of these data sets, and everything results in cuts, and then the tangle approach happens, hopefully. I mean, this is just guessing here. And then the last application, several people have mentioned that already. You want to classify molecules according to their chemical structure or function, or whether they are potentially a drug or something like that. So the objects are obviously the molecules. And the cuts could now, I mean, in my imagination, could be something like, does this molecule contain a certain chemical group that chemists know that's important? I don't know. A ring or something like that. I'm not a chemist, so you can ask all these questions about structures that you actually know as a chemist that might be important to characterize certain groups of molecules. So again, you get all these questions, and then you can invoke tangles. And the cool thing, again, I think in this example that's very obvious, this is where the background information of the domain knowledge goes into your approach. And this is what is in machine learning often so hard, to get this background knowledge into what you're doing. And here it is just so easy. Okay. So this is the story where we are now. I would say we're still at the very, very beginning, right? I mean, we have also this one paper which is on arXiv and got rejected a number of times. Anyways, that's a different story. But I think tangles are really cool. They are really flexible, as we've just seen on the previous slides. You get interpretable clustering. They are fast. They are sort of in accuracy comparable to other approaches. So on the first glance, there's nothing that's obviously wrong about this approach. I think now it could either be a downside or an upside. I think it's not an algorithm where you just press a button and out comes your result. Like spectral clustering, I mean, you compute the graph Laplacian, you tell the algorithm what is k, out comes your hard clustering. This is not what you would get with tangles, because with tangles, remember, you get this kind of soft pointing towards groups. So this is maybe not something that you would use as a pre-processing step for 50 million other algorithms, and it's just step 1 out of 5 million steps. I think that's not what tangles are used for. In my mind, it's more like if you have exploratory data analysis, you might want to discover groups, you might want to understand them, interpret them. This is, I think, what the strength of this approach might be. And there is obvious things that now need to be done. So the first things are more applications, like actually, but each of them is really a lot of work, because you have to do it with people who are in the field and try to show that it really does something in that field. We started that, but there's obviously room for many, many more. And then also from a theoretical point of view, there are many questions. And the one that I'm most intrigued about is somehow a relation to boosting. So if you step back a bit and think about what is it that tangles are doing, you have all these, maybe I go back to this very first figure. It's my last couple of words, don't worry about time. So this is the starting situation. You have objects and you have what we could call many weak cuts. So each cut just gives you a tiny bit of information. And now think about boosting, if you know what that is. You have weak classifiers, each classifier just being a bit better than random guessing. And out of many of these weak classifiers, you can combine something strong and get a very strong classifier with high accuracy. And my feeling is, or my gut feeling, what tangles do is something like that. So you have many weak partitions, each of them being giving you a bit of information about the cluster structure. And now we found this mechanism to use all these weak partitionings to get out, hopefully, a strong cluster structure, like in the block model or something like that. And I would love to prove a theoretical guarantee on that and try to formalize that. I don't know how to do that currently, but I think this would be really, really cool. It would be some kind of boosting for clustering, and it would just be great to prove that. Let's just go back. Yeah, and I think that was all I wanted to mention. Thanks for listening. I'm happy for questions.